to get into the nitty-gritty of how to size these tanks. And I like to go through the formulas. Again, the formulas are not complicated, but the key to getting this right is knowing where to get the information. So understanding what the inputs that are needed for the formulas is important, and how that ties in with the hydronic system, that's key. So let me draw our little schematic up here, where I've got our boiler and our pump, and then our closed loop system here, some kind of radiators up here of some sort. And let's look at this thing, and we'll do an example and size a tank for this system. So here's what the formula looks like. Volume of the expansion tank is going to be equal to volume of expanded liquid, and then what's known as the acceptance factor, 1 minus P min over P max. Alright, so we've just got three things we need to figure out. So let's say we're doing this example where we had 1,000 gallons of water in this system. We already looked at this earlier, that if we're heating water from 60 to 180 degrees, we're dealing with about 2 3/4% expansion. So that'd be 27.5 gallons of expanded water as we heat from that 60 to 180 degrees. So that would be our volume of expanded liquid. So we'll go ahead and plug that in, 27.5 gallons. Now we need to figure out this P min and this P max. So how do we do that? Well, you need some more information, more than what I've given you here. We need to know the height of this system. So let's say this particular system is 23.1 feet tall. I've chosen that height to make the math really simple here, because if you take a column of water that's 2.31 feet tall, you put a pressure gauge on the bottom of that, that gauge is going to read 1 psi. So the conversion there, 1 pound is 2.31 feet of water. So if I have a 23.1 foot tall system, my P min is going to be calculated by looking at what pressure it's going to take to get water to the top of that system. So 23.1 divided by 2.31, that's going to be 10 pounds. That'll get water to the top of the system. Now we need some additional pressure up at the top, because if we want to be able to vent air out of that system, we're going to need some pressure behind it. So typically what we do is we account for that by adding another 5 pounds. Now to make these formulas work, this guy is derived from what's known as the ideal gas law. And if this is going to work, this pressure ratio here, I've actually got to correct these pressures to absolute pressure. And the reason for that is, if I was to take a piston and a chamber and put a pressure gauge on this, and let's say I started off with 0 psig in that chamber, all right? Then let's say I took that piston and cut that volume in half. Well, the ideal gas law says that pressure would double. So if I have 0 psig start pressure and I double that pressure, well, 0 times 2 is still 0. So you can see with gauge pressures, the relationship for the ideal gas law doesn't work out. The math doesn't work. So that's why I have to correct these pressures to absolute. So that means at sea level I would add 14.7 psi A to that, and now I'm going to get 29.7 psi A. I'm going to round that to 30, and that is my P min that I would plug in when I'm doing these formulas by hand. Now, if I was doing this in one of the computer selection programs online, there I can plug in gauge pressure and I'll be just fine. Alright, so that's P min, has to do with the height of the system. Again, I'm figuring P min as my equipment and relief valve and fill valve is all down low and the system is above it. If something changes there, if all this stuff is at the top, then the height of the system, going down doesn't impact things. Let's look at P max next. What component in the system is going to help us figure out what our maximum pressure is? Well, of course, that's the relief valve. So I need to know what relief valve is sized for on my boiler. So let's assume it's a 30 psig relief valve on there, and we'll use that to calculate P max. Now, when I'm figuring out P max, I don't want to let my system pressure go all the way up to the relief pressure, or the relief valve will start to weep. It might not blow, but it'll start to weep, and then it's just going to sit there and want to drip all the time. So I like to take 5 pounds off there. And then I'm correcting to get me to PSIA. So I got 30 minus 5 plus 14.7. That gives me 39.7. And I'll round that to 40. So 40 PSI ends up being my maximum pressure. So 1 minus 30 over 40. I got 27.5. All that math goes to a quarter. So I end up with a 110 gallon tank. 110 gallon tank. Now, it's important to note that this value here, 27.5 gallons, and this value here, 110 gallons, are both significant when you're selecting a tank. One is the acceptance volume that's required. In other words, how much expanded water I have to deal with. I have to make sure that I have a bladder. You know, for example, if I had a partial acceptance tank, I have to make sure I have a bladder that would accommodate 27.5 gallons. So I need to meet both those criteria. I need to make sure my bladder can accommodate this expanded volume of water, but I need to make sure my total tank volume of 110 gallons is going to be adequate as well in terms of the air charge I need. So that is the basic idea on how you go ahead and calculate by hand a bladder style expansion tank.